Okay, so this is example program, Unit D2, page 5. Let's take a look at this problem. Okay, this is the water. Water flows from a two-dimensional open channel and is diverted by an inclined plate as shown in this figure. When the velocity at section 1 is 10 feet per second, what horizontal force per unit width is required to hold the plate in position? At section 1, the pressure distribution is hydrostatic and the fluid acts as a free jet. At section 2, let's ignore friction. Okay, so this program requires some background information actually to begin with. Okay, let's just consider, first of all, there is no such a thing called two-dimensional open channel. Open channel is always three-dimensional. So let's take a look at something like this. This is an open channel flow, 4 feet depth, and then flowing from left to right. Okay. Originally, there is a gate which is hinged right here, free to rotate around this hinge point. And then when the water hits here, it actually pushes open the gate. Okay? Then happen to be 20 degrees open, according to the figure. Then water is escaping from this opening. Okay? So before we move on, let's think about what really causes this gate to open. So that is the one question we have to really answer that. Well, obviously, if you have a water which has an open surface like this, now obviously the pressure within this water keeps changing because of the hydrostatic pressure variation. Okay? As a result, let's remember what we did in Unit B4. As a result, hydrostatic resultant force is going to be developed. Okay? So here we go. We are going to remember what we did. So basically, this is the surface of this plate submerged under the water. Okay. So this is the surface submerged under the water. So let's consider a unit width. Unit width means 1 feet. So per unit width of this plate, okay, well obviously you have this much rectangular area is submerged under the water per unit width, which is 1 feet. This is 4 feet. So that's the area submerged under the water. Because of so here is the centroid. Okay. Centroid of this area is of course 2 feet depth. Let's see. Okay. Well, what happens here? Well, you are going to develop hydrostatic resultant force, which is around here. You are going to create center of pressure. Okay. Hydrostatic resultant force is going to be developed. Okay. What is the rotation of this center of pressure? Of course, you know, 1/3 of 4 feet. Measured from bottom, 2/3 of 4 feet, measured from the top of the surface of the water. Okay, so this force pushes this gate and then opening this gate. Okay, so that's why this is going to be a steady state water keeps escaping from this opening, 20 degrees of opening. This opening is kept because of the presence of hydrostatic resultant force. Okay? So let's make this program simple. So let's assume that this Fr, even though this is turned 20 degrees, obviously, keep pushing this plate with the same magnitude. Okay? Same location of center of pressure, which is probably not true because now this is open with 20 degrees. Maybe this magnitude and location of CP probably changes, but let's not introduce those kind of complications. Let's just simply assume that center of pressure is still 2/3 or 1/3 measured from top or bottom of this cross-section area. The magnitude of Fr developed here is exactly the magnitude here. Keep pushing this plate up, keep opening this plate. Okay? So this force, hydrostatic resultant force, need to be included as a force in this program. Okay? So, question is, problem is asking you, so what is the horizontal force per unit width is required to hold this plate in place? Okay. So obviously you are going to find out horizontal force, which is anchoring force. Let's call this anchoring force FAX. That's right, anchoring force in the direction X. Okay. So what is the magnitude of this force? Of course, this one goes against this force and also force developed because of this momentum change also. So those two combined need to be supported by this FAX in X direction. Okay. Now keep in mind, this problem is not asking you to find FAY, y direction force. Well, we can obviously find that kind of force, but in order to find that, you need to know how heavy this gate is also, which is not given in this problem. But if I just modify this problem, of course, I can give you how heavy this gate is. That is going to determine y direction anchoring force also. Okay. All right. So obviously, this is only x direction component type of problem. Okay. Let's make things simple. All right. So first of all, I'm going to define my coordinate system. This is x direction. This is y direction. Well, probably the more better choice for this coordinate is z direction, goes against gravity. But again, I'm not interested in y direction force, so I just choose x and y. Okay. If this is the program to find out also FA anchoring force in this direction, you probably should choose this is x and z. Z being opposite to the direction of gravity. Okay. Obviously, it doesn't matter in this case because we are only interested in x direction component. That's why. So first thing first, I want to define control volume. So control volume, which is fixed in space. I'm going to include everything just like so. This is a fixed control volume. Okay. Now, as I choose fixed control volume, I automatically choose control surface 1, which is inflow, control surface 2, outflow. Okay. Then each control surface, you're going to define outward unit normal vector N1, output, toward the unit normal vector L2. This is obviously velocity vector v1, velocity vector v2. Okay? Now obviously, this control surface, this is a control surface 1. Velocity v1. Velocity v1 is u1i plus v1j, but this is only in x direction. How about control surface 2? This is a control surface 2. This is a velocity v2. Now, of course, velocity v2 has the two components. Velocity in x direction and y direction. So this is a u2i. This is v2j. Okay? So v2 is equal to, obviously, u2. u2 is 1. This is a 20 degrees. So u2 is magnitude of v2 sine 20 degrees I. v2 is magnitude of v2 cosine 20 j. Keep that in mind. This magnitude is going to be minus because it's going to go negative y direction. So this magnitude itself is negative. Let's be careful. Okay. So obviously I'm going to apply continuity and also momentum. Okay. So let's begin with momentum. Okay, since we are only interested in x direction force component, only thing you need is x direction component of the momentum. So, but anyway, let's begin with the momentum. Time rate of change within control volume v rho dv plus integral over control surface v rho v dot n dA is equal to summation of the force. This is a steady flow once again. So let's pick up an x direction component, x momentum. X momentum tells you that it's going to be integral over control surface 1. It's going to be u1 rho. Again, rho is rho of, this is water, unless it's constant. v1 dot n1 dA1 plus integral C control surface 2 u2 rho v2 dot n2 dA2 is equal to summation of the forces in x direction. Keep that in mind. Okay. Obviously, this Fr can be broken down into two components. Also, this is Frx. This is Fry. So I'm going to consider Frx, knowing that angle here is 20 degrees. Okay. So this is going to be obviously minus Fax, Fax being negative x direction. Fr cosine 20, right? That's Frx. Okay? So this is x momentum equation. Now, what is F1? Magnitude of F1. Do you remember the magnitude of F1? Magnitude of hydrostatic resultant force is pressure developed at the central location multiplied by the cross-section area. So remember, F1 is equal to PCA. PC is gamma times HC, hydrostatic gauge pressure, multiplied by the area submerged under the water. So this is going to be obviously gamma times HC is being 2 feet. So H1 over 2. H1 is being 4 feet. So this is 2 feet. Right? So this is H1. This is H2. Okay? H1 is 4 feet. H2 is equals 1 feet. Gamma times H1, 1/2 times, and cross-section area A1. Okay? So, X momentum equation becomes X momentum is, well, let's take a look at it. U1 is essentially magnitude of B. Okay? Magnitude of B. So it's going to be B1. Density is rho. B1 dot N1, if you take a dot product, gets you minus B1. Integrated over area A1 gets you A1. Okay? That's this term. This term. U2, what is U2? U2 is this one. U2 is whatever the magnitude of B2, sine 20. B2, sine 20. And density is rho. B2 dot N2. B2 dot N2. Just the B2. Integrated over area gets you A2. That's this. Okay? Must be equal to minus FAX plus this cosine 20 plus gamma over 2 H1 times A1 cosine 20. So this is X momentum you got. Now I want to apply also continuity as usual. So as usual, continuity is d dt over cv rho dv plus integral cs rho b dot nda is equal to 0. This is steady flow. So continuity applied on control surface 1 and 2. Actually, this is the water. So density goes outside, it's constant. Density goes away. This really is control surface 1, B1 dot A, B1 dot N1, dA1 plus integral CS2, B2 dot N2, dA2 is 0. This really tells you this is minus B1, A1, this is B2, A2 is 0. This really is Q1 is Q2. Continuity, right? So, continuity equation basically tells you relationship between velocities, okay? So this tells you what is the velocity B2 in terms of B1. B2 is equal to essentially ratio of the cross section A1 over A2 multiplied by B1. Okay. Let's consider unit width. In other words, cross-section area A1 is H1 times unit width. Cross-section area A2 is H2 times unit width. So this VD is H1 times 1 foot divided by H2 times 1 foot per unit width, right? So conclusion from continuity is B2 is equal to H1 divided by H2 times B1. So now we want to combine those two equations. Let's call this equation 1, equation 2. Okay? So let me just secure a few more spots. Combining equation 1 and 2. So those two equations combined, okay, you can determine FAX. So FAX is going to be 1/2 of gamma times H1 squared times cosine 20 plus B1 squared rho times H1 minus H1 over H2 times B1 squared. By the way, this is B2. B2 can be represented by H1 over H2 times B1. Sine 20 rho times H2. So this really is the equation combined by equation 1 and 2. So you can plug in the values. So gamma of water is 62.4 pounds per cubic foot divided by 2. H1 is 4 feet. Take a square times cosine 20 plus B1 is 10 feet per second. Take a square density of water 1.94 slug cubic foot minus ratio of H1, H2. H1 is 4 feet. H2 is 1 feet. Times B1 is 10 feet. This whole thing square multiplied by sine 20 degrees multiplied by density again 1.94 slugs per cubic foot. Sorry, I'm out of space, so it's over. Can you hear? H2 1 feet. Okay? So I just plug in the value. Sorry, I just ran out of space, so just multiply by that. Continue. Okay? Therefore, what is FAX? If you plug those numbers in, you should get, let me double check. Something wrong. H1 is missing, sorry. This row multiplied by H1 4 feet. Sorry, I'm missing this H1 here. Multiplied in. It's hard to fix now. I realized H1 was missing, so this H1 is here. So row multiplied by 4 feet minus H1 over H2 times B1, whole thing squared times sine 20 multiplied by, sorry, let me do it off. I don't want you to confuse, so I just fix it completely. Sorry about that. So okay, so this is okay 1/2 of gamma. H1 is 4 feet squared. sine 20 plus B1 10 square density, okay? Multiply by H1 is 4 feet. Okay? Subtract H1 over H2. 4 feet divided by 1 feet. Multiply by B1, 10 feet per second. Square, or that square. Multiply by sine 20 times density 1.94. Slug per cubic foot. H2, 1 feet. Okay. So that's the good picture, better picture here. Hence, if you plug in all of those values, compute, you're going to get FAX. This is the X component of the anchoring force required. 183.46 pounds. Okay, so let's go back and take a look. That is the X direction component required to support this plate. Now, if I give you extra information such as weight of this plate, you can obviously determine the Y direction component to support this plate. Y direction component. That is actually weight of this plate balances against this FYI. Yeah, that's right. So, okay. Yeah, that's right. So that means weight of this plate is precisely equal to FYI. That's what it is. Okay, that's good. FAX is essentially supporting FRX and also X direction component of momentum change. Both. Okay. Now, if I include the weight of this liquid, that actually contributes to the Y direction component of the force. So FAY is essentially this one plus Y direction momentum change based force development. So, but this is particularly the problem which is interested in how much force you need to support this plate in place. Okay. Now keep that in mind. This is not an easy problem. We need to all understand what causes this plate turning and then escaping the water out from this gap. What is the mechanism? The mechanism is hydrostatic resultant force developed. Really is pushing and keep pushing this plate to open the gate. Okay? This is quite challenging problem.